In the second section of chapter 2, we consider two new types of the limits, namely infinite limits and limits at infinity. Infinite limits and vertical asymptotes are used to describe the behavior of functions that are unbounded near x equals 0, x equals a. Limits at infinity and horizontal asymptotes are used to describe the behavior of the function when x assumes arbitrarily large positive value or arbitrarily large negative value. Although we will include graphs to illustrate basic concepts, we postpone a discussion of graphic techniques until the next chapter or chapter 4, I don't remember, okay? So, let's start from the infinite limits. Infinite limits. The graph of f of x equals 1 over x minus 1. Actually, we can sketch this graph easily. Let's show that. This is similar to the graph of the 1 over x, just this is the shifted version to the right side. So this is the x equals 1 line, vertical line, and the graph like this one. This is the graph of the function f of x equals 1 over x minus 1. You can observe easily limit when x approach 1 from right hand side, 1 over x minus 1 does not exist. Actually, since x is bigger than 1, x minus 1 goes to 0 from right hand side, positive part. So 1 over x minus 1 goes to plus infinity. But that means the limit does not exist. There does not exist a real number L, because it's infinity, that the value of the f of x approach when x approaches 1 from the right. Instead, as x approach 1 from the right, the value of the f of x are positive and became larger and larger. That means f of x increase without bound. By making some observation, calculating the some values of the function, you can observe this situation. We express this behavior symbolically as the following way, okay? So we say limit x goes 1 from right hand side, 1 over x minus 1. This does not exist, but we write equals infinity, or f of x approach infinity when x goes 1 from right hand side. Since infinity, this symbol, is not a real number, the limit, this limit does not exist. We are using the symbol infinity to describe the manner in which the limit fails to exist, and we call this situation as infinite limit. We use the infinite notation to describe the positive growth without bound. We use the minus infinity to describe the negative growth without bound. and we use the from the left side of the graph, you can observe from here, when x approach 1 from right hand side, it goes to minus infinity. So we can use the minus infinity notation. So limit x goes 1 from left side, 1 over x minus 1 equals minus infinity. Or f of x goes to minus infinity as when x goes 1 from left side. We use also the following notation, minus and plus infinity notation. Okay, that means this is infinity or minus infinity. Infinity or minus infinity. If, actually I mentioned here from the graph I showed that, if x approach 1 from the left, the value of the f of x are negative and became larger and larger in absolute value. That means f of x decreases toward negative value without bound. Again, by making some calculation, you can observe this situation. There is a calculation in your textbook you can find for these values. But from the graph you can observe. So we express this situation according to this limit or this explanation. According to these two limits, we can talk about the one-side limit. One-side limit describes the behavior of the graph when x goes to 1. From this figure, you can observe. From left side, it goes to minus infinity. From right side, it goes to plus infinity. Does the two-sided limit of f of x when x approach 1 exist? Actually, this does not exist. Okay, no, because neither of the one-sided limit exists. Also, there is no reasonable way to use the symbol infinity to describe the behavior of the f of x as x approach 1 on both sides of 1. We say that the limit 1 over x minus 1 does not exist. So we can express this situation, limit when x goes 1 over x minus 1 does not exist. You cannot say this is either infinity or minus infinity. Why? Since limit when x approach 1 from right hand side 1 over x minus 1 different than the limit when x goes to 1 from left side 1 over x minus 1, because left side is plus infinity, right side is minus infinity. If these are equal at the infinity or minus infinity, actually these are not real number, but if this approach infinity and this approach infinity, you can conclude this limit is infinity. You can use this symbol. Again, limit doesn't exist, but you can use. If both limits are minus infinity, you can use the symbol minus infinity. For example, let's give the quick example. G of x equals 1 over x minus 1 square. Now, when x goes to 1 from left hand side, g of x is plus infinity. And when x approach from 1 from right hand side, g of x is again plus infinity. So according to this fact, why it goes to plus infinity? According to the previous observation, we can say that although it goes to minus infinity, we have a square, so x minus 1 bigger than x minus 1 less than 0 when x approach 1 from left side, but x minus 1 square bigger than 0. So x minus 1 square goes to infinity, 0, 1 over 0, but this goes to positive infinity, so it goes to plus infinity. So here this goes to plus infinity. Maybe I can explain briefly. Limit x goes 1 from left hand side 1 over x minus 1 square. We have this function. So here x goes 1 and x is less than 1. So x is less than 1 implies x minus 1 less than 0, but x minus 1 square bigger than 0 because we have a square. So this is bigger than square, bigger than 0. And when x approach 1, this approach 0. So this is approach to 0 from right side. So 1 over 0 goes to infinity. So this goes to plus infinity. So this approach infinity, plus infinity. So as a result, limit when x goes to 1, g of x is infinity. Again, this means doesn't exist, but you can use notation infinity to describe the behavior. Now we can define the infinite limit and vertical asymptote. The vertical asymptote the vertical line x equals a is a vertical asymptote for the graph of y equals f of x if f of x goes 0 or f of x goes minus infinity. One of them is enough when x approach a from right hand side or x approach a from left hand side. That is, if f of x either increase or decrease without bound as x approach a number a from the right or from the left. How do we locate vertical asymptotes? If f is a polynomial function, we have already discussed, then limit f of x is equal to the real number f of a. So a polynomial function has no vertical asymptote. Similarly, a vertical asymptote of a rational function can occur only at the 0 of its denominator. In the previous lectures we mentioned. And also we gave some easy calculation for this situation. So let's repeat that situation as a following theorem. So if f of x is a rational function, n of x over d of x is a rational function. In the previous course, we say d of c equals 0 and d of c equals 0 and n of c different than 0. Then the line x equals c is a vertical asymptote of the graph. Why? According to this definition, if dx goes to 0, dc goes to 0, so this statement implies us limit when x goes c, n of x over d of x goes to either minus infinity or plus infinity. Why? Because d of x goes to 0, n of x goes to some value L, which is different than 0. So L over 0 goes to either infinity or minus infinity according to the sign of the L and according to the approach of the d of x side d of x to 0, okay? Sometimes d of x approach to 0 from left side or right side. If n of x and d of x equals 0 at the point C, then we have a 0 over 0 indeterminate form as we mentioned before.